Hello everyone. Hello everyone to Bilecik Algebra and Number Theory Seminar. It's my pleasure to host Luis Victor Dieulefait from University of Barcelona, and he will talk about safe chains of congruence between Galois representations, a tool for modularity and functoriality. Thank you.
Okay, so first of all, thank you very much, Ilker, for the invitation to speak in your seminar. It's a pleasure to have the opportunity to see you again. And so I want to speak about the talk is going to be my plan in a great part of it a bit informal in a sense. I prefer not to go to the technicalities, but to just try to convey the general ideas. Yeah, I will even start with some historical, I don't know, introduction to the subject. So everything will be related to this Galois representation, which are or should be, according to these conjectures, in many cases attached to modular forms or more general automorphic representations. In all cases, there will be Galois representations somehow coming from geometry or having the same nice properties as those coming from geometry. So as I say here, you see in the slide, this is part of what I'm going to present, is showing work with Javier Guillan. This is at the end of the talk. I will try to give some details about some particular case of base change, which is done in this work with my student, Javier, who is finishing his PhD working on these base change problems, okay? And then if at some point of the talk I mentioned some joint work with other people, I will also mention the corresponding collaborators. But so let me begin, as I say, with a kind of historical introduction. All this business, say, all this story of connecting geometric Galois representations to modular form, we can say that it started with the modularity conjecture for the case of elliptic curves. So this in the 50s, Yutaka Taniyama and Goro Shimura, they were working with both elliptic curves and modular form, and they came with this surprising connection. I will present the conjecture in a drawing in the next slide on how to connect elliptic curve. For the moment, it's just elliptic curves over the rational numbers with classical modular forms. So this is the picture I want to mention. In principle, the conjecture should be the one in the horizontal top row, which is, on the one hand, you have an elliptic curve over the rationals, and then on the other hand of this horizontal line, you have a classical modular form, which is assumed to be cuspidal Hecke eigenform of weight 2. The level of the modular form, we call it n. It should agree with the n, which is the conductor of the elliptic curve. Then you also have the same invariance, the A sub p, which are these numbers that you know well for elliptic curves. This number that you obtain counting points over over finite fields should also agree with the coefficients A sub n of the modular form, which are the Hecke eigenvalues or the Fourier coefficients. So the conjecture is what is put there, modularity conjecture in red, which is that to any elliptic curve you can attach a modular form having the same number, the same A sub p's, the same conductor, etc. Of course, it will be a modular form whose A sub n are integers because you want to match them with these numbers, which are the A sub p's of the elliptic curve. So in this situation, it is known that for such modular form, if you assume an integral coefficient, there is an elliptic curve that is part of, say, the standard results of the theory, and then the conjecture is to go on the other direction, for an elliptic curve, attach a modular form. And in the picture, I put this, what I call the golden triangle, because I put a third actor, which is the Galois representation. There is this compatible system of Galois representation. If you take them from the elliptic curve, they're describing for every L, you have an L-adic representation describing the action of Galois on the L-adic Tate module of the elliptic curve that you obtain from torsion points of order L to any power. And so, elliptic curves give rise to Galois representations. Therefore, you can think that the modularity conjecture, you can think of it as saying that to such Galois representations, you can attach a modular form. A particular thing, you can observe that if you think this way, then you can have this representation for just one L, because the information on this representation is not depending on the particular L you pick. This is what is called a strongly compatible system, because you move the L, and basically you are just changing the topology, because you go to the L-adic numbers with different L-adic topologies, but all these representations somehow have the same information. They have the same A sub p's, which are now the traces at unramified Frobenius, the same conductor of the system. So it's a system that behaves very nicely. They were introduced by Serre in his book in the 60s. This notion of rational systems of Galois representations. So they behave very nicely, and so somehow the modularity conjecture is like saying that you believe that these geometric Galois representations are modular. But this is like thinking the conjecture in a different way. But I think it's important to mention this because this is the way the conjecture was proved. The conjecture was proved, the elliptic curves were proved to be modular by showing that the Galois representations are modular. So this third actor, the Galois representation, is really very important because it was the linking bridge that was built in order to finally match elliptic curves with modular forms. Okay? So that's the first conjecture. Here I just have, if you want, very briefly, pictures of the people who were involved in the proof of Fermat's last theorem. We are not going to discuss Fermat's last theorem, so it's just as a remark, which is very, very important, that this modularity conjecture in particular was key, and it was proved because one of the motivations was that at some point it was realized that it was enough to deduce Fermat's last theorem. So as I say, we are not going to discuss much Fermat. Let me just show you very briefly what are the actors involved in that very important kind of results. So first was Yves Eliowarch, who saw that to a solution ABC of Fermat's last theorem you can attach some elliptic curve with very nice and strange properties. So this was the Eliowarch elliptic curve attached to a solution. So here A to the P, B to the P are part of a solution to Fermat. So you're assuming A to the P plus B to the P is also a P power. And then you build this elliptic curve. So it was, especially the strange property occurred with the P torsion, where P is the prime P in the exponent. So the P torsion is generating a Galois extension with surprising properties. So somehow he started to realize that it shouldn't exist. They give rise to an extension of Q, which somehow, if you match its ramification with the size of the extension, it shouldn't exist. Okay? So then this was kind of pulled forward by Gerhard Frey, who really realized that the important connection was with modularity. So he realized, okay, so if now we assume the Taniyama-Shimura modularity conjecture, which means that you believe in particular that these elliptic curves, the Eliowarch-Frey elliptic curves, are modular, then this really, really should help improving Fermat's last theorem. But that depended on certain properties of modular form that were not quite clear. I mean, the connection was very mysterious because the link was through properties of modular form that were not proved. Somehow Frey conjectured that modular form has nice properties. Then Serre formalized a little bit this property. It was the birth of Serre's conjecture was here. In particular, the epsilon conjecture, which is part of Serre's conjecture, was what was needed to make precise this idea of Frey. And it turns out to be a property of modular form that eventually was proved by Ken Ribet. It was the property of level lowering. Modular form has this property that Frey has kind of guessed and Serre has formalized. And because of this property that Ribet proved of level lowering, that will be related to what we're going to see next in other parts of the talk, then it was clear that modularity of elliptic curves and Taniyama-Shimura was enough to deduce Fermat. And then, as you know, the end of the story is that after 7 years of hard work, after knowing the result of Ribet, Andrew Weiss, they said the bravest man because he coped with all the obstacles and managed to prove modularity, to prove the Taniyama-Shimura conjecture, and then in particular to deduce Fermat. So this is just for you to see one of the main motivations of this modularity machinery, say, is that you can apply it to Diophantine equations. I will not go any further into that, but in particular it was key to deduce in 1994, 1995 that Fermat's last theorem was true. Okay, so we are going to say a few words about the important part for us of all this story of Fermat, which is a bit of the ingredients that were used by Weiss to deduce this modularity of elliptic curves, because this is the inspiration to what's going to follow. All these things that I want to present about safe chains of, or if you want, congruences of Galois representation, started here. You will see in one of the tricks that Weiss has to apply already started. But first of all, in any situation where you want to prove modularity, now you want to prove modularity of elliptic curves, you are Andrew Weiss, then you need some starting point. And for him, it was very important to work. Remember that if you want to prove modularity, it's enough to prove modularity of one of these Galois representation attached to the elliptic curve. So he considered the particular case of the prime p equals to 3. So he looked at the three-adic Galois representation. Um, as I said before, proving modularity of each of them is equivalent. So why he took p equals to 3? For the following reason. If you reduce modulo 3, so you're looking at the action of Galois on the three torsion points, now the image of this residual representation goes to GL2F3. And the key point is that GL2F3 is a solvable group. And solvable groups are very particular, right? Historically, we know uh, in, 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 in the 19th century, there was this huge distinction between solvable and unsolvable groups. There was how solvable groups were created because the solvable case was the one that you can handle with radicals, no? The solvable equation. But here in the universe of modularity, this distinction between solvable and non-solvable also shows up, in particular because of a work I'm not going to explain, which is complementary, if you want, to the ideas of Weil, the works of Langlands and Tanner, where there's also related works by Clausel and Arthur Clausel, that in many situations when you deal with solvable extension, you can prove modularity. Okay, it has to do with what is called solvable exchange. So in any case, the important thing is that because results of Langlands and Tanner, the fact that GL2F3 is modular implies that this residual representation is modular. But what is the meaning to say that the residual one is modular? You wanted to prove that the three-adic representation is modular. The meaning is, when you say that the mod 3 representation is modular, what you're saying is that it has a modular lift. In other words, what you have is a congruence between your given three-adic representation attached to an elliptic curve and one coming from a modular form. This is what you get because GL2F3 is solvable. And that's the starting point. You know that you have a congruence with something modular. At least you have something. So your coefficients A sub p, you don't know that they're attached to a modular form, but you know that they're congruent modulo 3 to those attached to a modular form. It seems like a very tiny little piece of information, but for Wiles it was enough. And so the machinery that he developed is a machinery saying that if I have a congruence with something modular, I can prove modularity. Okay? Under technical assumptions, of course, but he managed to deduce from this modularity. This is what he called the modularity lifting theorems. Modularity lifting theorem, here is the general framework, is that if I give you a p-adic representation, in his case was p equal to 3, if you know that it's congruent to another p-adic representation which is modular, then under certain technical assumptions, including of course the necessary conditions, which are the so-called geometricity condition for your representation, then the representation is modular. This is the framework of the Wiles modularity lifting theorems. If my p-adic representation is congruent to one which is modular, then it is modular. And this is what he applied to the case of an elliptic curve modulo 3. Okay, where the congruence was known because of Langlands and Tanner, and then he managed to construct all this powerful tool technique and then deduce modularity of the elliptic curve. This is the main idea. So in the work of Wiles, we see that because of the technical assumptions, he needed to develop an auxiliary trick, which is very important for what I will explain later. First, let me comment that the work of Wiles has been generalized since his first result by many people like Diamond, Fujiwara, Taylor, Savitt, and Kissing. Okay? And in particular, as I say, if you work with a p-adic representation, you should put the necessary conditions, those that are known to be satisfied by the modular representations. This is what I call the geometricity conditions, okay? And they include that the representation should have a finite ramification set and good local properties at P. It should be what so-called the p-adic representation locally at P should be the RAM. They also should be continuous and not, etc. Okay? And then there are technical conditions that Wiles need to impose, and these other people also need to impose, that usually have to do with local conditions, such as ordinarity, and also restriction on the size of the residual image. Typically, you want the residual image to be big in many of these theorems as a technical condition to prove the theorem. Okay? So, in his proof, in particular, Wiles needed to assume that the mod 3 representation was irreducible. So, let's say he already happened to prove modularity for elliptic curve, but only under the assumption that the mod 3 representation is irreducible. That is not enough. He wanted to prove for more elliptic curves. Okay? Sorry, is there any comment? Can I continue? It's okay? So, okay, later, and I mentioned this because it's important to know, in the generalizations of this theorems of Wiles, for example, there's the theorem of Skinner and Wiles, and more recently the theorem of Pan, this condition was removed. So nowadays we know that even if the residual representation is reducible, you do have this kind of theorems, okay? But the time that Wiles was proving this result, he needed irreducibility. So what was the trick that he employed to succeed? He showed that if the material representation is reducible, then he can make his elliptic curve to be congruent modulo 5 to another elliptic curve. So the 5-adic representation attached to elliptic curve is going to be congruent to the one attached to another elliptic curve. And so to make this short, he managed to prove all these conditions, that there is a congruence modulo 5 with another elliptic curve, such that the other one has irreducible mod 3 representation, right? And then he also knows that he can assume that the mod 5 representations are irreducible. So somehow he managed to translate the problem to another elliptic curve. Okay, there is another elliptic curve E prime. So for the other elliptic curve, he can prove modularity because he shows that the other one is going to have an irreducible mod 3 representation, right? And then the modularity of E prime is somehow propagated to the modularity of E through this congruence modulo 5. So this is just the first time that you see these congruences to propagate. Instead of proving modularity modulo 3 directly, because he cannot, he says, okay, I do a congruence modulo 5 to switch to another elliptic curve, then the other elliptic curve, modulo 3, has big image, so I further use modularity of E prime, and because of the congruence modulo 5, he applies again the modularity theorems otherwise to deduce the modularity of E. So somehow we start to see that moving, switching the prime, and doing congruences can be useful. In a very, very tiny, if you want, example, which was called the 3-5 trick, because he was just playing modulo 3 and modulo 5. What we're going to do later is playing the same game, but we're going to work modulo many, many primes, playing lots of congruences to move around. But this is like the first time we start to see this kind of movement. Okay? So, mm, uh, okay, here is just a comment saying that when he proved the modularity theorem, this was called, the technical part was called a patching argument. He did it in collaboration with Richard Taylor. Then there was the work of Brill, Conrad, Diamond, and Taylor that generalizes, improved this result so that all elliptic curves over Q were known to be modular. And then there were generalizations by other people, including myself, that allowed to deduce modularity of other geometric objects, right? And then other people also proved modularity of elliptic curves over quadratic number fields, real quadratic number fields, etc. By generalizing these results, many new modularity theorems were obtained. But we're going to discuss here something a little bit different than that, not just geometricity of specific geometric objects. Here, in this slide, is just to present the fact that classical modular forms are a particular case of a wider class of objects, which are automorphic forms. And in this context of the Langlands program, usually you want to study geometrical representations, and sometimes you want to you conjecture that they will be attached to classical modular form, but sometimes you conjecture they will be attached to more general automorphic form. So in particular, if you just change your base field from Q, the rational number, to a totally real number field, the analog of a classical modular form is now a Hilbert modular form. Then you have all the same theory here. You have Hecke eigenform, Caspia Hecke eigenforms. You have Galois representation attached to those. But now the Galois representation of G sub F. G sub F denotes the absolute Galois group of F. So by changing Q, and instead of Q, putting F, now the context is more general. Now you are dealing with Galois representations, as before, two-dimensional representations. But now of F, these are Galois representations attached to Hilbert modular forms, and you have similar modularity conjectures. For geometric objects, like elliptic curve, for example, defined over F, you will conjecture that they are modular in the sense that they should be attached to Hilbert modular forms over F. Okay, so the generalization of classical modular forms and modularity now is, for us, is by changing Q to another totally real number field. There are more general variants, but we're not going to discuss them. So we stick to the case of classical modular forms versus Hilbert modular forms. The only thing that changes for us is the base field. So it doesn't matter what is the generality you want to work. You can stay over Q, you can work over F. But here I'm just putting what are the modularity conjectures, which are generalized in Taniyama and Shimura. So the Langlands program in general, what predicts is a relation between, as I say, on one hand, classical and Hilbert modular forms, And then on the other hand, if you want two-adic Galois representation, two-dimensional, sorry, Galois representations coming from geometry, from smooth projective varieties. Okay, so this can be disclosed as follows. You can say that you have the Fontaine and Maisel conjecture. We somehow say that sufficiently nice abstract Galois representation should come from geometry. And sufficiently nice means this condition, finite ramification set and locally the RAM. And then Langlands, which predicts that this representation should be modular. If you put the two together, you get the so-called Fontaine-Maisel-Langlands conjecture, which is, for the purpose of this talk, the more general modularity conjecture we are going to consider. And basically saying that anytime I give you a two-dimensional continuous representation of the absolute Galois group of F into GL2 QL bar, you assume it's odd, irreducible, and with these nice local properties, the ones that Fontaine and Maisel kind of knew that are specific to representation coming from geometry, um, then this representation should be geometric and should be modular. Modular means attached to a Hilbert modular form. So this is the general modularity conjecture. Somehow you have two-dimensional representation which are nice, two-dimensional representation which are coming from geometry, two-dimensional representation which come from Hilbert modular form. They should be the same. Being locally nice, coming from geometry, so attached to a smooth projective variety, like the ones attached to elliptic curves, or being attached to a Hilbert modular form, the three things should amount to the same. This is the realm of the modularities conjectures. So in this talk, the rest of the talk will be about discussing instances of result with proof cases of these modularity conjectures. There is also the mod p variant of this conjecture that is missing. And then there is another aspect which is called functoriality in the Langlands program that I'm also going to discuss one particular case of it. But basically, this is the context we are moving, the Langlands program. Here is the modularity conjecture. Now, let's say one more, which is self conjecture. It's a similar modularity conjecture, but now you state it for a representation in characteristic P. So now, for simplicity, I will state it only for the case of Q, which is the case that Serre conjecture. Later it was generalized. So this is a representation which I call rho bar of the absolute Galois group of Q, but now it's going to GL2 of a finite field. So K is now a finite extension of Fp. And again, we have a representation which is odd and irreducible. Because the field is finite, it's automatically continuous, so it has finite ramification set. I mean, these conditions that I put here are enough to conjecture that the representation is modular. So it means that it's the mod P representation attached to a modular form, or if you want, that it has a p-adic lift corresponding to the p-adic representation coming from a modular form. So you see, modulo P representations should also be modular according to the conjecture of Serre. When he formulated the conjecture, he specified a couple of invariants. I will call it N and K, which are called the Serre's level and the Serre weight. He explained how you compute these invariants using the theory of, I don't know, conductors of number field, conductors of Galois representations of number field, etc. And then he specified this N and this K, and they're somehow minimal under certain assumption that you don't include ramification at P in N. Under this convention, let's say, they're kind of minimal. And so it is important, or maybe worth mentioning, that the fact that he's specified this strong version where he say that what should be the level and the weight where you're going to find a modular form given this lift, it's also helpful when you prove the conjecture. So the fact that he formulated a stronger version was useful in the proof. And the story of the proof started with a result, an unexpected result, if you want, of Richard Taylor, which is called potential modularity. And this is a result that you can apply in this setting, either if you're interested in the modularity of a p-adic representation or you're interested in the modularity of a mod P representation. In both cases, Taylor proved what is called a potential version of this result. And so here is Richard. And so let us state a bit informally, because it's a bit technical, what is the result that he proved, this potential modularity. Somehow you are working with a representation rho sub P, which is a p-adic representation, as the one that I introduced before. So suppose the rho sub P is a representation that you believe is modular. It has all these conditions in the Fontaine-Mason-Langlands conjecture. What he managed to prove, under certain technical assumptions, is that it is potentially modular. So there is an extension f, totally real, of your base field, in this case of Q, such that you can put local conditions at P, but in particular the important thing is that the restriction of your representation to GF is modular. So it is attached to a Hilbert modular form over F. And this also applies to a representation with values in a finite field like in self-conjecture. So for all the modularity conjecture that we have been discussing, what Taylor proved is that he's not proving the full modularity conjecture, but he proved that there is a restriction to some extension of your base field, such that when you restrict your representation to the absolute group of this extension f, which is kind of not specified, it's not computable if you want, it's just existence of a suitable extension, such that when you restrict, then it is modular over there. So corresponding to a Hilbert modular form over f. So the result of Taylor, it has, when he proved, he already got some other application. I will not go into that. It was useful in particular in the proof of Sato-Tate conjecture, so he has some applications for it. But then some people, including myself, we realized that there were other applications of this. Applications for modularity, which is a little bit unexpected because he's proving this potential modularity, which seems to be a little bit like a weak result, because you can say, okay, the restriction to an extension of degree 1,000,000 is modular. How can I use that to deduce modularity over the base field? The important thing was that this result was so strong that it allowed us to deduce important properties for the representation that eventually were used to deduce modularity. So this is the story. This was the key result. Without this result, the proof of, for example, of search conjecture was completely out of reach. But because of this potential modularity, here what I call how to facet a gemstone, because somehow you have a gemstone and you want to make into a jewel, right? And you have to facet it. You have to, from potential modularity, which is like, you know, this gemstone that you want to work with, you want to deduce modularity, which is some finer thing. So Caleb, Intermercier, and myself were among the people who realized that this was probably looking a little bit like a weak result, but it was very, very strong. And actually, using this result, we managed to deduce that representations, modulo P or p-adic representations, because they are potentially modular, they share a lot of properties that were previously only known in the universe of representation that were known to be modular. Okay? So here are the two results. One result is minimal lifts. If I give you a residual representation like the one in self-conjecture, now at least, because of potential modularity, you can prove that there is a p-adic lift, for example, which is minimal. It's not introducing extra ramification. And it is also very nice. It's crystalline. So meaning there is a lift as the one coming from the modular form you are searching for. You are not proving it's modular, but at least there is a lift. Because in Galois theory, it's very difficult to deform a mod P representation to a p-adic one. Okay, this is immersion problems in Galois theory that are completely non-trivial, right? I give you a group as Galois group, this group as Galois group over Q. This group is a quotient of another group G prime. It's not easy to realize G prime as a Galois group over Q, knowing that the quotient is a Galois group. And here you want to deform GL2FP to GL2ZP, which is an infinite extension. You had a lot of intermediate steps to go on, right? People working exclusively in Galois theory, like Ravi Ramakrishnan, have been able to prove that these deformations exist, but at the cost of introducing extra ramification. Maybe you need to introduce 1,000 extra primes. So it was very, very difficult, and actually recent results were only there to prove the existence of a lift, but here you can prove the existence of a minimal lift, a lift that is not introducing extra ramification. And believe me, the only way you can do this is because you have potential modularity. Okay? So in particular, this is the analog of Rivet level lowering, meaning that now you can prove Rivet level lowering without modularity. So it's a very twist of events, because after this, now you can manage to, somehow Rivet was a result that was needed to whiles, but now you can prove Rivet somehow using whiles, because first you can construct the minimal lift, and then you can use whiles technique to prove that the lift is modular. So how it's a little bit strange how things go, but here you can manage to produce minimal lift, which was the content, if you want, of level lowering, without knowing modularity. You see, there were properties exclusively known in the modular world. This was the key point that modular form has this magical property that was used because of Fry saw it was an important property, Rivet proved it, and it was key to prove Fermat. It was exclusive for modular form. Now it's not exclusive anymore. After representations, they do have minimal lifts. And then once you have a p-adic representation, you want to start to move in compatible systems, like Weil did when he switched from 3 to 5, etc. And in the proof of cell conjecture, moving from one prime to another is also very important. Otherwise, you are stuck into this p-adic representation. You construct the p-adic lift, and you're stuck in this p-adic representation. You can do nothing more. But if you can move in compatible systems, you can move to other primes, and start what you will see is an induction argument. And this is because the second conclusion of potential modularity is that p-adic representations, which are nice, the ones that are conjectured to be modular, even if you still don't know they're modular, they do belong to compatible systems, like the ones attached to elliptic curves, like the one attached to modular forms. So nice p-adic representation, now you can deduce, because of potential modularity, that you can put them in strongly compatible systems. So you can move the prime, right? Which, by the way, was a result that if you read this book by Serre in the 60s, which was called something like abelian L-adic representation, he put it as a comment. He was describing these compatible systems, and then he made like a comment or a question in the book saying, should it be possible that nice p-adic representation, perhaps they always belong to compatible systems? So this result was like an answer to this question of Serre from the 60s, saying yes, these nice p-adic representations, they do belong to compatible systems. By the way, the notion of nice was the notion introduced in the Fontaine-Mason's conjecture in the 90s. So the comment of Serre from the 60s was a bit informal. He was kind of saying, yeah, I mean, geometric representation, I mean, those coming from geometry, they should probably be the ones that you can put in compatible systems, okay? But in any case, the important thing is that in the context of modularity, in the context of Serre's conjecture, it was potential modularity, the result of Taylor, that was key because it allowed to prove these two results, which now I call the mobility result, because they are the two results that allow you to move. It's important, the minimal lift, because it allows you to move having a control on the ramification. Because if you have to make a lift introducing 100x ramification primes, it's not worthy because you lose control. I mean, anytime you lift, introduce extra ramification. But because the lift is minimal, you always keep control of the same ramification set. And then because you have this compatible system, you can move from one prime to another. And then I will not give you the details, but the proof of Serre's conjecture is based on these two results that I just mentioned, the mobility results. The modularity distance theorems are wise, they are played all the time. Each time you do a congruence, you want to apply the modularity distance theorem otherwise to propagate modularity. And then an induction arguments. So basically, very briefly, the idea will be, I mean, I have to say that the result was proved 20 years ago, but recently, like 2 years ago, for example, with Ariel Pachetti, we explained that something similar to what I'm going to explain now, that because the modularity distinctions otherwise now are much stronger, the proof gets much simpler. And so the proof I will present here briefly somehow is similar to the proof that you can get today because it's much easier, you have a stronger modularity distinction, so it's close to reality. It's still, I will do some simplification, but so the idea is that if you want, you just say that you take a minimal lift, you have minimal lifts, then you move in compatible systems, and the idea is that you will move in a compatible system, you will move to a prime p sub 2, so you go to the p sub 2 adic representation, which is a prime that is in your conductor. So if you have 100 primes in your conductor, you move to one of them, and when you reduce modulo this prime, somehow you are killing this prime. Just by definition of the invariance, somehow when you reduce modulo p2, like for free, you are getting rid of one of the primes in the conductor. And then you can take another lift without this prime in the conductor. So somehow just for free, moving to p2, reducing modulo p2, you can take a lift without p2 in the level. So it seems very, very ideal, the situation, because for free you have removed one prime from the level. And the important thing is that in this congruence modulo p2, you are getting rid of one prime in the level, is the very strength of the theorems, the modularity distance theorems of Wiles, that allow you to do this, because you will have a congruence and you will be able to propagate modularity from one to the other. Somehow this is the induction that kind of for free, because of all these results that we have, allow you to remove one prime of from the level, from the conductor n, and you do this one at a time, until you reach to level 1, to a situation where the level is 1. Okay? So this seems very easy, but because you are using 3 very deep results, which are the 2 mobility results and the modularity distribuciones a la Wiles, um, the ones, as I say, that were available 20 years ago require so many technical conditions that life was much, much more complicated than this. But today they have been improved in such a tremendous way that it's more or less as simple as I'm explaining, that you are reduced to the situation of level 1. Okay, this is what I call killing the level. Okay, you just go and kill the primes in the level one after the other. Just combine these techniques: minimal lifts, existence of compatible systems, and modularity distinctions otherwise. And so that's how you are building a series of congruences, because of all this possibility you have to move, until you reduce the proof of such conjecture to the case of level 1. And when you're in the case of level 1, you have a compatible system, situation of level 1, and then you say, okay, now I go to characteristic 3. Because when you reduce modulus 3, you can see that also the weight can be assumed to be small. So by reducing modulus 3, we have reduced to level 1 and also to weight 2 or 4. Again, for free, because modulus 3, you will make a congruence to something else, now having a small Serres level and small Serres weight. So if you believe in this, you have these very strong tools. All the proof of Serres conjecture is reduced to a situation where the level is very small, level 1, and the weight is also only 2 or 4. And the characteristic is 3. And this is the starting point. This was another, let me call it, seed. Because as happened in Wiles, you always want to prove modularity, you always need a seed. Remember, Wiles was in a situation where, because the elliptic curve has rational coefficients, when you reduce modulo 3, you end up in GL2F3. And GL2F3 was solvable. Therefore, you have Langlands tunnel saying this is modular. But here the situation is different, because when I reduce modulo 3, maybe I end up in a field of characteristic 3, but having 81 elements. So GL2 of F81 is not solvable, okay? So you cannot apply, like Wiles did, Langlands and tunnel. But what you can do is you can say that you are in characteristic 3 again, but also the conductor is 1. And luckily here, I found out, surprisingly, that for this prime, for this level, Serres conjecture was known. Okay? I was at the very beginning, Serres conjecture was not proved. I was trying to prove Serres conjecture. But then I realized that at this point, um, I mean, at the beginning, I was dealing with these basic cases of small conductor, a small n, a small k. In characteristic 3, Serres conjecture, I found out it was known. And actually, before explaining, okay, I will skip this one. I will only put this picture. This picture is about what I call scaffolds and a bridge. It is just for what you will see it a little bit later, than the process that I described just here for the proof of Serres conjecture is a little bit oversimplified, because at some point there are technical conditions you cannot deal with. And for those, what you do is you introduce extra ramification. You put this somehow a scaffold, right? You put extra ramification just to get rid of the technical condition, and then you remove it. Okay? As I say, that when you build a bridge, you want to put these false work, these scaffolds, and then you remove them, and then at the end you have your wonderful bridge there. And they were put as a tool that you use in the process. Okay? So to be honest, they will not appear here, but they will appear later. In the process of proving modularity, sometimes it's convenient to put some extra ramification, okay, to introduce some extra prime in the level, just as a scaffold, okay, just to make things, to make images bigger of residual representation, etc., and then you remove them, okay. So for the moment, I just show you the picture of this scaffold. And so what I was saying is that here there was this induction, and let me just finish the induction, the seed. The seed, is there any question? Okay, so the seed is the case of level 1, weight 2, and in characteristic 3. And as I say, in 2003, I was thinking about this case, and I found out that this case was solved. Was solved in the 70s by Serres himself. And actually, the proof was 2 lines. You will see the proof in 2 lines. In the marginal note, this is the page and the volume of Serres collected works, where it was proved that in characteristic 3, representation of conductor 1 has to be reducible, So in particular, this was enough for modularity. It has to be T plus 1. So this was enough to initiate the proof of modularity. And so here you have, I put a copy. I don't know if you can see the last two lines in comment 229. He said that in characteristic 3, he's using this bound for discriminants to prove that these extensions in characteristic 3 of conductor 1, eventually he proved that n is equal to 2. It means that it's at most a quadratic extension. So it is 1 plus the modulus 3 quadratic character. It's an extension of degree 2. The only possible extension of conductor 1, I mean ramifying only at 3, which values in GL2F3, which is odd, etc. It has to be this quadratic extension, and this was enough. So somehow the base case for Serre's conjecture that was needed was proved by Serre in 73, generalizing this result of Tate. Tate proved it in characteristic 2, and Serre just made the comment in 2 lines that the same result of Tate also works well in characteristic 3. Okay, so this is the story of Serre's conjecture. And again, as you see, you need some seed to start propagating modularity, and here is the seed. Okay, the basic case is level 1, weight 2, and characteristic 3. It was known. Okay, but it's very specific of this situation. Okay, as I show in this picture, it's like the tree of life, right? This is the tree of life in the theory of evolution. Life started from this very primitive form of life, the last universal common ancestor, and then it propagates by evolution. Here, modularity follows the same pattern. It started from this quadratic extension 1 plus G3, which is attached, if you want, to some, to some modular form in a certain sense. It's a character. And then it evolves by congruences. So the theory of evolution is replaced here by all these congruences that allow you to link all the representation to each other and to propagate modularity. So in the rest of the talk, I will explain how this idea of congruences that was used in Serre's conjecture can also be used to prove more things in the Langlands program. Here it was used to prove modularity by doing some induction, okay? But what if you want to do base change, okay? Base change is another prediction of the Langlands program, and now the idea is not that difficult to understand what's the meaning of base change. It means that if I have a classical modular form, F, any classical modular form, so you have 2 ingredients here, a classical modular form, little f, and a totally real number field, capital F. Okay, these are the 2 ingredients. What I want to prove is that any classical modular form can be lifted to any totally real number field. And the definition of lifting a modular form to the field F, let me put one definition, there are several equivalent ones. It's just to say that there is a Hilbert modular form attached to the base change of F to F. In other words, if I look at the Galois representation attached to my classical modular form, when I restrict them to the absolute Galois group of capital F, then they are modular, they are attached to some Hilbert modular form. So, in other words, I give you Galois representations over Q which are known to be modular by assumption. I restrict them to any totally real number field, and I want to prove that the restriction is also modular. It's attached to a Hilbert modular form. And this is what I proved. It was a result that was proved by Langlands in the 80s in the case of solvable extensions. Again, we see that in situations where the Galois groups are solvable, there were tools from the 80s allowing to prove modularity and to prove base change. But what I did is to prove in full generality for any totally real extension using the machinery of Wiles. Okay? And basically, what I will show you is maybe some pictures without being too technical, for you to see how using congruences, you can again prove that this is true by the similar strategy. It will be true for some specific modular form for some previously known reason, and then you can contagiate this to any other modular form by congruences. That's the idea, okay? So the idea is here is the theory of congruences between modular form. What I will prove, which is something that was also a new result, is that if you consider all modular form, all classical modular form, I mean Hecke eigenforms, remember, they have attached Galois representation. I give you any one, any pair, F and G. And you have the Galois representation rho F and the Galois representation rho sub G. Any pair of modular forms and the corresponding Galois representation. Then what I prove is that you can find a chain of congruences linking them. So there are intermediate modular forms, F1, F2. You start with F, then you have F1, F2, Fn, Fn being G. You start with F, you finish with G, you put these steps in between. Some primes, T1, T2, Tn, and suitable congruences linking this. So you have somehow, you start with F, and you can make a congruence between F and F2 modulo a prime T2, then F2 is congruent to F3 modulo T3, and so on. You have congruences, congruences, congruences. You start with F, and you finish with G. In between, you put some auxiliary modular forms and some auxiliary primes, and you have congruences. So what I prove is that you can find congruences linking any pair of Galois representations. Okay? But these are not any congruences. They should be safe congruences. Safe was in the title of the talk. And what is the meaning of safe? Safe means that you can apply the theorems of Wiles. Okay? So the idea is the following. If I can link any pair of modular forms, suppose for a moment that the form G, I pick a form G that for some reason is a form where base chain is known. This form G is a form already having the property. So it's a form G such that when you restrict to the Galois group of F, it is known to be modular. It is known to be attached to a hero modular form. Okay? Then using all these congruences that I have just show you the forms in between, what you need to say is that because your representations are congruent over F, the restriction to F are also congruent. You're restricting representation satisfying certain congruencies, the restriction also satisfies these congruencies. And because you start with one which is known to be modular in the restriction, if you can apply a modularity listing theorem a la Wiles over the field F, now you're thinking about modularity listing theorems over F in the language of Hilbert modular form. Then you propagate modularity to the restriction of the other one. Okay? So you have this chain of congruences. You look at the congruences between the restriction. One of them you assume is modular because you assume base change is known for this one. And then this restriction, they propagate modularity one to the other because of the magic of modularity listing theorems. Okay? Therefore, you need to ensure that these congruences are sufficiently nice. You have to build things in a way that any pair of modular forms are linked through suitable congruences, but also in such a way that these congruences satisfy the necessary condition in order to apply the modularity distinctions a la Wiles. These are called safe congruencies. So you build a safe chain of congruencies. Therefore, using that, you are able to deduce base change. And let me just tell you that the case you use as previously known is a form with complex multiplication because it is known since the time of Hecke and Drinfeld. Sorry, sorry, I forgot the name. Since the time, let's say, of Hecke, that forms with complex multiplication, they do satisfy this base change property, just because they are linked to Grossen character. Okay? Therefore, this is the G you pick, the basic case. You manage to link all to each other, any pair of them. In particular, you propagate from the ones that have the property, the one with complex multiplication, to any other one. You do go and you propagate modularity. So I think I don't have much more time. Maybe my final comment can be that if I can show you a picture of all these congruences that I use in this context to connect, but it's a little bit technical. I can just mention that here you will see, if you see the detail, you will see again the scaffolds. In order to connect safely any pair of modular forms, you put extra ramification in order to make sure that the residual images are big, which is part of the technical condition that you need to apply these results a la Wiles. So here the scaffolds are very, very important. And in particular, I have my own industry of building small scaffolds somehow. Because you want to keep the scaffolds, but at the same time you want to end up in a space sufficiently small so that you compute the modular forms and you see the links and you compute all the links. And my last comment will be that with my student Javier Guillan, we are doing similar things, but now instead of starting over Q, we start over quadratic number fields. And still starting over certain quadratic number field, we also have been able to do the same strategy, the same machinery. Therefore, for one number field at a time, I have to say the method is very specific because it requires a lot of computation. For one number field at a time, we managed to do this, to connect all the modular forms so that you can start there saying that some of them having the base change property, then you connect them all, you propagate, and all of them eventually you can deduce base change for all of them. Okay, but here, for simplicity, I have started with the case that you have classical modular forms over Q, and if I can show you one picture, here is the picture about connectedness, because um, let me just mention that this is a result that we prove with Ariel Pachetti, and we prove it over any totally real number field. So this one doesn't require computation. So what we prove is that if you start with in any number field, totally real, all Hilbert modular forms are connected. But in that generality, we cannot prove that the connections are safe. We just prove that there are ways of connecting through congruences, okay? But if you want connections to be safe, that's something you have to do like by hand, one field at a time. This is the distinction, okay? And so maybe the final picture will be the picture of what we were discussing, the classical. And here you see, you start with an arbitrary modular form, which is your F. At the end of the row is your form, which is Cm, the one with Cm having the property. And you manage to link any pair of representations, the one attached to any classical modular form F with one with Cm, using just transitivity. So the induction here is to reduce the weight and the level until you end up in a space with small k and n. But because of transitivity, you are connecting your F and your modular form with Cm, both with a space with small level and weight. And that space here that you see on the right of the slide is the space of weight 44 and level 17, etc. It was the chosen one because it's a space with a unique orbit of modular form. So everything gets connected there. It's a unique one. On one hand, there is a unique orbit, but on the other hand, ramification is big enough because of this level, so that you manage to end up there. And even in the last congruence of this chain, the images are big. So all this chain is safe, and it allows you to link any pair of modular forms through this small space. Okay, the induction is done to end up in a space with small k and n, but not because in the small k and n you have a case where the base change is known, but because of transitivity, this is like the middle point if you want to connect any pair of modular forms. In particular, you connect any pair, you connect any F with one with Cm. So through the full diagram that you see here, you propagate modularity after base change, which is what you want, from the Cm1, which is below, to an arbitrary F, which is above. And that's the way of deducing this modularity of the base change to any total real number field of any classical modular form. And in particular, this little prime 43 that you see in the level here in some intermediate modular form is what I mentioned before, my method of introducing small supercuspidal primes in the level is what I call a micro good dihedral prime, which is something again new. I mean, you develop a lot of new techniques, in particular how to put scaffolds, tiny little scaffolds in your level to ensure big images. It's like doing level racing, supercuspian level racing at a small prime. So I wrote a paper on that, how to do supercuspian level racing at a small prime, which was not known, but somehow was something needed for this procedure. Okay, so I think I will stop here. So if you have any questions.
Thank you very much for this nice talk with good illustrations and historical background. Thank you very much, Luis. Are there any questions or remarks?
Can I ask a question? Actually, two questions.
Sure.
One of them is just a few slides ago, you said that there is a connection between, if you choose any two Hilbert modular forms, there is a connection.
Yes.
Does this connection respect Langlands functoriality?
Yeah, I mean, the problem is the following. We can manage to connect any pair of Hilbert modular forms over your given number field, but at some point, very briefly, at some point, the first part is something we control a lot and we can do it safely. We manage to put the two of them in a common level and weight. In particular, we can make it a parallel weight 2 and in a common level, right? And once you are there, we rely on a result of Mazur saying that Hecke algebras are connected. So there is a theoretical result there that tells you that once you're in this fixed weight 2 and fixed level, then the graph will be connected. The forms in that space will be connected. But you don't know what's happening, meaning that those congruences, you don't know that they are safe, meaning that in those congruences you don't know if you can apply the theorems of modularity that you require because you want to propagate modularity through each congruence, right? For example, if you want to do base change, if you want to do symmetric power functoriality, no matter what is the functoriality you want to prove, you will be applying some modularity lifting theorem to certain avatar of your representation, namely the base change or the symmetric power or tensor product or whatever. But you need to control the congruences. So there we rely on a theoretical result. The result of Mazur that we kind of, the extension was kind of trivial. I mean, the same proof that Mazur gives works over totally real number field using Shimura curves. I mean, so in particular, we know that they are connected, but you don't know how good it will be. Over a specific number field, you can compute things. It takes a lot of work, but eventually you manage to prove, if you're lucky, that you end up with something which is safely connected or something similar that is enough for your purposes, okay? And then you can go. But the bad part of this method, as you can see, is that there is a point where it becomes computational. It is bad in a sense because, as I say, you have to work with one field at a time if you want to ensure this. For the moment, we don't know how to improve this.
Thank you. So my second question is more in some, I just got this idea. When you described potential modularity,
Yes,
so potential modularity is like we have a certain finite index subgroup of
yes,
GLQ where we
exactly.
have modularity. So
Yeah.
can we do some sort of uh, group induction argument and apply some Mackey theory to get
Mm. That's what I did, and that's what Taylor did. Taylor used what you are saying to deduce the meromorphic continuation of the L function.
I see.
Because he,
Yeah,
but
yeah,
he, as you can guess, you are using also the intermediate fields so that the intermediate groups are solvable. I mean, on top.
right,
So
right,
because your group is kind of generated by the solvable subgroups, yeah, and because of, as you say, Mackey theory and Brouwer theory, uh, you use the fact that in solvable subextensions you preserve modularity. So it's not only modular on the top field, but it's also modular on intermediate fields such that this group is solvable. So you have a lot of intermediate modularities. And that is what he used to prove the meromorphic continuation. You get the meromorphic, you get the denominator. In this virtual sum, you get the denominator, the sum,
right,
you know. So this is what he uses for Sato Tate. This is how he got the meromorphic continuation of the function from potential modularity. And then I used the same techniques for the existence of the compatible families, again because of Mackey formalism and Brouwer
yeah,
formalism. Yeah, yeah. So somehow you use all of that. Ideally, you will like to try to use this, for example, to say, okay, in the universe of potential modularity, now you know that they are all connected. Even if, as I said 30 seconds ago, you don't know that connections are safe, at least you know that they are connected, right?
right,
So ideally, you would like to say, why don't we try to say that because potentially we know that they are connected, that after representations being potentially modular, they are also connected. That we haven't succeeded yet, but it's part of the conjectures. If I can put just the picture here, all this Rayuela conjecture, we wrote with Pachetti, is a conjecture saying that abstract representations should also be all connected to each other because they are modular, presumably. So the
right,
Rayuela conjecture is like equivalent to the modularity conjecture because in the modular universe, we already know that everything is connected. We proved that generalizing Mazur. So we say the Rayuela conjecture means that now everything, abstract representation should also be connected. It's clearly a conjecture is equivalent to modularity. But perhaps this is the path to prove modularity. I feel that if someday someone proves modularity, will be through this approach, right? So what I say is that what is missing is what I say is Jacob's ladder, which is we have been able to descend from heaven, from the heaven of potential modularity. We have been able to descend a lot of results, like we were discussing the existence of minimal leaves, the existence of compatible family, etc. It remains to descend from the heaven of potential modularity the connectedness. And once we have descended the connectedness from the heaven of potential modularity, then modularity of everything will just something that will follow from the modularity listing theorems. I mean, there are technical conditions, of course, but descending this, not descending directly modularity, but descending only the connectedness phenomena, I think will be the main step. The main remaining step is to be able to descend this connectedness that is in the previous slide using potential modularity. So potential modularity is telling you that if you go to certain extension, your restrictions are all connected. And now you want to descend this connectedness, like these angels that are descending from heaven. And that will be it, I believe. So it's perhaps something that is going to be doable at some point. But who knows, right? That's the hope.
Do you have any idea about non-solvable case? Because solvability is kind of very central in all the theory.
Yeah, what I mean here, in any solvable case, everything is known. In a
Yeah,
solvable case, the descent,
yeah,
everything, the big change in the two direction is known
right.
by the work of Wiles. But my idea will be that, exactly what I just said, that you should be able to use potential modularity together with the connectedness in the universe of modular forms. You should be able, there, I don't know, I mean, I don't know how to prove it yet, but there may be some idea. You should be able to descend the connectedness so that eventually you manage to connect representations like in the Rayuela conjecture, okay? And once you connect representation, as I say, this is not enough to prove modularity of any representation of the total real number field F because of the technical conditions in the congruences. Once they are connected, you can say, oh, but yeah, but if you want to apply the modularity between zero and a while, there are technical conditions. But the technical condition, you can hope someday will be all of them removed. I mean, you can dream on that, or you can dream on doing things better, as I did in the case of base change. You can maybe do things in a certain way so that you also manage to connect safely. You also manage to make things in a way that you can handle I mean, you can force the congruences to satisfy the nice conditions so that the modularity distinctions otherwise can be applied. And of course, these are the kind of things that people that work in this, we are thinking, and there are tricks to try to do things this way and the other. And this probably is the way that is going to end up being the general modularity conjecture being solved at some point. But for the moment, we are just, doing what we can more and more.
Thank you very much. Excellent talk. Thank you.
Thank you for your questions. They're very interesting.
Thank you. Are there any questions?
Yes. First of all, thank you for the great talk. It's very inspiring and also makes things approachable and understandable and possible to appreciate the whole technical machinery that you're describing. I would like to. One question is you were focusing on these congruences that form these steps in forming the path.
Yes.
I'm wondering if these congruences, we can interpret them in some higher and maybe global algebraic object, algebraic structure, as the relations that are that we mod out by in some freely generated structure. And if we can build such a global object, then maybe the local information is being actually transferred to a global object, and maybe that machinery can help clarify the picture. And secondly, again, thinking along the lines of this notion of connectedness, I'm wondering if it seems to suggest that there should be corresponding to this global object some at least one and possibly more cohomology theories that would count the connected components and give information about this problem. And what do you think if there might be such a theory?
Okay, so I have to say that the first of your questions reminds me of some thoughts I had at some point. Because, for example, if you want to know the way that Taylor managed to prove potential modularity, is because he showed that the restriction of the representation is realized over a suitable extension in an abelian variety of GL2 type, something similar to an elliptic curve, but also he managed to prove that it's an object such that he can force the existence of another prime Q such that modulo Q, that abelian variety has a small dihedral image where you can get modularity from, say, Langlands and Tunnel. So somehow he's working with abstract geometric objects, which usually, I mean, they come from a certain moduli problem where you always have points over Q bar, and he managed to prove that you have points over a totally real extension with some nice local properties, etc. So it's a very high-level result. The one that he proved is very abstract because he's saying, using this theory of Rumely and Moret-Belli, he's just saying that I mean, this is a moduli problem after all. I want to get a deformation of a Galois representation, but he wants it to get it from some abelian varieties so that modulo another prime is small image, so it's modular. Like in the 3-5 trick of Wiles, he's doing a PQ trick somehow. Okay, this being said, what I was thinking at some point is maybe these chains of congruences I want to build can also be interpreted as some geometric object in the sense that what I want to. The problem is that I don't know how many primes, I don't know what are the primes, so it's a little bit difficult to formalize. But basically, you can say that what I'm trying to construct, you can also say that I want to construct something like not one abelian variety of GL2 type, but many of them. I mean, suppose that all the representation that I'm putting in my chain of congruences come from abelian varieties for simplicity. I'm trying to find like a very huge moduli problem because I'm saying I want to find existence of n abelian varieties which are congruent to each other, and I'll build in my path, you know? So probably a geometric interpretation of my problem in that context can help solving it. The problem I have when with this approach is I don't really know how many forms you have to put, what are the primes. So it's kind of difficult to formalize. But perhaps if at some point someone comes with a right way to formalize this, that can be maybe a way to prove what we were saying, no? The existence of these chains of congruences, this Rayuela conjecture. Maybe there is a geometric way of formalizing it. Um, and as for the number of of irreducible components or connected components, um, as I say, eventually the conjecture is that there should be just one connected component. Everything should be connected to each other. And I haven't thought about what you're saying in your second question other than that. Is that answer your questions? I mean,
Yes, somewhat. Do you think there, I mean, in regards to the second question, can you sort of, if at all possible, speculate on such a possibility? So this kind of resembles in algebraic geometry, you have, a curve like the idea of moduli space, a curve whose points themselves are curves, or the collection of
yeah.
all varieties of a certain satisfying a certain property themselves form a variety, etc. And
Yeah.
then there is cohomology theories that would
Well, yeah. I mean, that's what I say. Yeah, now I understand better. I mean, yeah. In some sense, I think that your two questions are related.
yeah.
And basically, the answer will be that perhaps you're right that giving a right moduli interpretation to all these questions can be useful. So somehow, maybe thinking the chains as or I don't know. There are many possibilities, but in general, putting the moduli problem interpretation to the problem to try to see if we can find the existence of this chain of congruency through points of certain variety, classifying certain problems. See, I don't know. I haven't explored it because when I tried to do this, since I didn't know how many forms you will have in the chain, I mean, maybe I'm not proficient enough so that I don't know. I just had it at the level of raw ideas, let's say. But
Well,
perhaps,
I mean, same here, more or less. I feel the same way.
yeah, yeah. But
I
yeah, it could
understand.
be in the same way that, as I say, historically, when Taylor proved this result, he was using these abstract theories of Rumely and Moret-Belli, and eventually they were useful. And maybe 5 years before he was mentioning this, nobody had even thought that this abstract approach could be of any help. And eventually it was. So, I mean, mathematics work like that. So why not?
Thank you. And in relation to Professor Ikeda's question, to what extent can, if we have a non-solvable case, to what
Mhm.
extent can we reduce it by forming a solvable series or something?
No, as I say, the problem with you can use Brouwer formalism, etc. the fact that somehow you can relate a group with the solvable subgroups. But as far as I have tried, it was very useful, for example, to prove the highly non-trivial result that you can put your representation inside compatible systems, because several of the restrictions were modular. Therefore, you can put this restriction into compatible systems. So at the end of the day, I managed to show that the existence of the compatible system containing a p-adic representation. So you're given a p-adic representation for one prime, and you manage to put it in a compatible system, like in the case of elliptic curves, because you know that this is true for the restriction. I mean, the formalism has been applied to that. I have tried to get other applications, but I haven't succeeded. Of course, the first aim of Richard Taylor when he proved potential modularity was to try to prove potential modularity in such a way that the extension was solvable directly. But you know, solvable fields, the collection of all solvable extensions of Q is not a large field. And you are using here the theory of large fields in the technical sense. And he needed something, you know, a large field. So unfortunately, the collection of all solvable extensions is not a large field, right? Very unfortunately. I think that if you put the collection of all extensions of Q of odd degree, that give you a large field if you use certain result of Coyote-Leng. But then they're odd, but they're not Galois. If you can put together odd with Galois, odd and Galois will be solvable, and that will do it. But if you put together all odd extensions, unfortunately, because they are not Galois, that will not be good enough to reduce to the solvable case. So I mean, mathematics is always difficult, but I have been trying to play with other large fields, tricks like that. Many tricks have been applied. Sometimes you kill the p-zero because the p-zero is solvable, and you can make solvable exchange just to assume that your extension has a degree prime to p, which is sometimes having degree prime to p is very useful for these immersion problems, because where the kernel of reduction modulo p is a p group, so if your extension has degree prime to p, it's much easier to extend results from the top to below. So you kill the p-zero sometimes. I mean, of course, you play with all the group theory that you can. You can assume that your prime is unramified, so that local conditions are preserved, again, by killing inertia group, which are solvable. You play all the games that you can using group theory, but and maybe the relation between a group and all the solvable subgroups can be used more. I mean, I don't know. I mean, I don't know what to say, but probably thinking better and thinking more, you can do more things. For example, when Langlands and Tanner result we mentioned before was a result that Langlands proved for the cyclic case, and Tanner extended for the S3, which is non-cyclic, thinking a little bit more. There are some cases where people prove this kind of result in non-Galois extension by considering a little bit of group theory, going to the Galois case, and I'm thinking of results of Harris on base change in non-Galois extension. So playing a little bit with the group theory maybe can give you a little bit more in certain situations, yes, but I don't see how to do better.
Thank you. Thank you very much.
Thank you. More questions or remarks? Actually, very nice discussions, very interesting. You have some thank you messages on the chat. So actually, it seems that it's likely that we don't have more questions or remarks. So thank you very much for the speaker again. Thank you, Liz. It was our pleasure.
Thank you for the invitation and a very interesting question that helped me to learn more and to think more about this, because they were very interesting.
Very natural and very good.
Yeah.
So for some announcement for the next semester, our preparations are almost set, and actually we will start in more likely in March with new speakers. We will inform you with emails. You can also check our webpage. So see you in the next seminar, and goodbye.
Bye. Thank you.
Bye.
Ciao.
See you all later.